welcome back to Decouple for a much anticipated part two of a recent episode examining Vogtle and the nuclear renaissance that wasn't. James, it's been fabulous. We've had lots of feedback to that first episode. People are really clamoring for the follow-up that we did promise them. It's been a couple weeks. It's always good to make people wait a little while, right?
Of course.
But thank you for taking the time to come back on.
Yeah, no, I'm glad to, sort of report here back from the Death Star that I'm currently sort of recording this in. But, I think that, there has been a lot of feedback to the episode. And one of the things that I think is most interesting about the Vogel and Summer saga is, where the community has responded and hasn't responded. And I want to take maybe a second to think about how we are all thinking about where we are in the nuclear space right now and how Vogel and Summer fits into that narrative. I think as, from the 30,000 foot level, if we wanted to talk about what went wrong at Vogel, we would basically say, Westinghouse hadn't completed the design yet. The EPC hadn't completed their part of the design. That's the first major problem. We had a second challenge in that we did not have a supply chain that was ready to supply a modular plant like Vogel at the quality that was needed and on the time and schedule accuracy that was needed. And a third issue was that we hadn't built a nuclear power plant in decades in the United States. And we had a general, lack of familiarity of the workforce with, building things at the level that is needed for a nuclear power plant build. But I want to put this now, zoom out from that and just talk about where we are today in 2024, right? Where we see that there is no new nuclear power plant under construction in the United States. None. There's some test reactors that are being built for the advanced or the yet to advance, to use your recently coined term, or NOAA's recently coined term. And we have some, light water reactor projects going on in Europe, particularly Hinkley Point C, that are not exactly, obviously not AP1000s, but are not exactly a stunning success so far. And I think this should all cause us a moment to pause, pull back, and ask the question, have we really learned the lessons that are available to us from Vogel, Summer, OL3, Flamanville 3? And are we, as a community and as an industry, are we actually taking those lessons and rapidly trying to learn from them and ensure that we don't repeat the same mistakes? And I think that advocates in particular have some responsibility, not responsibility, but in some ways, this is one of the most important tasks that advocates can do, which is ensure that we are accurately seeing what happened and ensuring that it won't happen again. And that I'm not so sure is happening. And I think some of the response to this episode on the more critical side maybe exemplifies that, as well as we'll go into some of the sort of myth making or that has surrounded this project in light of the fact, in lieu of the fact that we haven't had a major sort of lesson learned report that has been issued by the industry about what went wrong at Vogtle 3 and at Summer 2 and 3 that we could utilize to publicly ensure both customers that this won't happen again, but also make sure that we don't make the same mistakes.
So, and the topic of that lessons learned side of things and the industry being transparent about it, I'm not sure if I heard it from you or somewhere else, but I do understand such a document exists. But apparently, to kind of access it, you need to get into Fort Knox, go through a whole number of security clearances, leave your phone at the door, sign NDAs, etc. Was that just a rumor I heard, or is that
I
something
think it's
behind
a
that?
rumor. I've heard that rumor as well. What I'll say is I have never seen such a report that exists.
And
The
you've
rumor
tried.
is I
there's
think it might be
there's
even.
not many people
I've
that try harder
tried.
than you, I
The,
think.
yeah, there. I think maybe the Nuclear Energy Institute or the American Nuclear Society has such a report. I don't think it's publicly available. One of the things that is really, really clear is that if you go and talk to American utilities and American independent power producers, they don't really understand with much detail what happened at Vogtle and what happened at Summer, why it will or will not happen again. And so this is a major, major barrier, I think, to new nuclear in the United States right now. And, one of the things that I talked about in the last episode was I mentioned a sort of piece that Rod Adams made about blaming the aircraft impact assessment rule. And I wasn't saying that the aircraft impact assessment rule wasn't a major driver of this, of course. What I was saying is we can't say that the aircraft impact assessment rule, which was not applied in China, that the NRC, which does not exist, doesn't have authority in China, when it took China 9.4 years of nuclear construction to get an AP1000 online, which is, three standard deviations longer than what the 42 recent large light water reactors, they built. We can't blame the NRC for the root cause of this, nor can we blame the aircraft impact assessment rule for the root cause of this, because we took away the root cause and we got nearly the same outcomes. And those outcomes also, I mean, what's amazing about the Chinese example is not only the Chinese on a median build a reactor in 5.5 years, the Sanmen and Haiyang builds didn't happen during COVID, right? Whereas Vogtle 3 and Vogtle 4 had to go through COVID, which was a major disruption of productivity. It didn't go through they have a labor force that is highly, highly able to build nuclear power plants and churn them out in a 5.5 year sort of timeline. This really was, to a large extent, not saying there wasn't challenges and major challenges induced by the regulator, but this was primarily, I would say, a result of the industry not really being able to deliver a project. And we shouldn't shy away from that fact, because the only way that we can ensure that the industry will be ready for the next project build will be to really, really ensure that the lessons that happened at Vogtle and Summer, which are a treasure trove of lessons learned, are understood, socialized and, capitalized upon in the broader community and the broader industry. And this applies not only to AP1000 projects, but AP300 projects, BWX 300, just general nuclear project builds. This is really, really important. And we need to have a much better story to be able to tell other people who are considering building new nuclear as customers about what happened, and can't just say, oh, it was the Nuclear Regulatory Commission's fault, because they are they're about to make a multi-billion-dollar investment. They can see the same information that I can see, that China somehow wasn't able to build it either. They didn't have an NRC nor an aircraft impact assessment role on time and on budget. So let's really actually be serious about this. And, there's some other examples that we could dive into about the sort of myth making that has happened in the community around Vogtle and Summer, if we're interested to dive into, that I think sort of just show this compulsion of, I think, not compulsion, but maybe understandable impulse of a lot of nuclear advocates to sort of blame other folks, external sort of forces, for the challenges that we faced in this build.
Yeah, no, absolutely. I think, as we outlined in the previous episode, having this case control experience over in China, hugely, hugely helpful to start breaking down what are the relevant and most important variables. Last week, or I guess it was a couple weeks ago, we were really, putting ourselves in the perspective of, had we been there in 2005, what would this all have looked like? Could we have seen it coming, essentially? And this episode, we talked about sort of moving into the noughties. I think we're still going to be drawing comparisons between China and the US, but getting a little bit more into the specifics of the projects at Vogtle and Summer. So, unfortunately, I spent all morning, arguing over this silly post on advanced and yet to advanced reactors rather than preparing for this much more important episode, James. So I'm going to let you sort of steer it in terms of the architecture and hopefully pipe in somewhat intelligent ways throughout.
Right. Yeah. So I mean, we can restart back to, I think we sort of ended pretty early in the sort of experience. I think before even nuclear construction started, where we just saw the sort of supply chain starting to break down at the Shaw Modular Factory over in Lake Charles, and we really started to see the project just become, behind schedule, because we weren't able to supply the modules that were necessary to build the plant on time and on schedule. And one of the things that I think is important, as we talked a little bit about, is that even these large modules, right, are broken down into dozens and dozens of submodules. And this is a necessity not in all power plants, right? But in the place, for example, Vogtle doesn't have navigable barge access directly at the site, which means that we would go to maybe the port of Savannah or another port and sort of drop off the sort of submodules and then ship them by land, right, to the site. And this would turn out to be one of the major differences that if you do a historical comparison, as we start building out the comparisons that we had compared to other sites and other previous project builds. In particular, I think the advanced boiling water reactor builds that we saw in Japan, that everyone sort of keeps as this example of, hey, we're able to build large light water reactors in 38 months, 36 months, maybe even. Why couldn't we do that the same thing? Well, one of the things, and this is not one of the things that they did there is they completed the design impeccably before the project build was done. But one of the things that also is a direct comparison, a direct difference, excuse me, is the fact that in that build, right, what we saw was the modules, right, being much, much larger and literally being barged up to the site. And then the large lift crane literally taking those modules directly off the barge and shipping them, sort of moving them maybe a couple thousand feet over where they need to be placed in the site. And what was the difference here is that when we have even those modules when they arrive from Shaw down in Lake Charles, say CA20, right, they had to be then assembled and built in a module assembly building, right, and welded together, and then shipped, sort of moved over to where they would be placed in the plant site. And this is a contrast to what we have seen in other sort of pre-modular Generation 3 builds that may have been more successful. Now, this doesn't explain all of it, of course, right? The Chinese builds did have direct sea access directly to the site, and that didn't make that much of a difference. But one of the things that we talk about when we're talking about modular construction is the idea that we can literally be building these things in factories. Well, not only did the factories fail in the Vogtle and Summer builds, at least initially, and they were unable to deploy those submodules on time and on budget, we started to see the fact that we had to build a whole new factory called the Module Assembly Building at the site, right, in order to assemble those submodules into the big modules that would be placed at the site. So one of the things that I think that we should all be looking for when we're looking at, where do we want to deploy the next large light water reactor, things that seem quite, how do I want to say it? Very practical, much less exotic than, say, how, a molten salt reactor would be built or, core neutronics. But the very basic logistics of how we're going to ship things and what the size that we're going to be able to ship things to at the site really should be a critical factor, or one of the critical factors that we look at when we're elucidating or sort of distinguishing what the attractive elements of a site are and not at a site. Because this turned out to be a sort of interesting issue that was faced at Vogtle. Now, in the defense of the Vogtle workers, there's a lot of the submodules that would arrive at the module assembly building, and they would be at such a low quality that they would have to literally be re-welded. Even the work that was done at the module at Shaw, let's say, you literally have cases of workers having to grind out the welds and re-weld them to basically meet the QC. So in many cases, having this module assembly building at the Vogtle site was a blessing, and having that sort of experience of a craft labor workforce that was able to do that module assembly and integration was a really great thing. But it shouldn't have been necessary. Right? We should have had a supply chain that really was ready to do it, and a logistics sort of delivery chain that was able to do it in a way that minimized on-site work that needed to actually get those modules ready to be placed and on hook.
So modularity is definitely a major theme here, and I don't want to skirt it at all whatsoever. Maybe we'll come back to it, but maybe before we do, just for those of us with a little less experience with nuclear construction, I mean, I watched a video of sort of a time-lapse video of an ABWR being built in Japan, which is pretty miraculous, but it just gave me that little bit of perspective on, okay, what actually goes into building a nuclear power plant. Obviously, there's a whole bunch of excavation, there's a base mat pour, there's the NSSS, balance of plant containment. I don't know if you can, if this is too much for a podcast, but if you can take a minute or two and just describe, what the various steps are, just, from really 30,000 foot view. And maybe, from Vogtle or in general, what seem to be the challenges? I've heard, again, basing on that MIT work, that the NSSS is actually not, a major cost driver, but is it a time driver, et cetera? I just want to get a sense of, what the 5 or 6 steps are. There's probably far more than that, but ground our
Yeah, I
listeners a
think
little bit before we dive in.
breaking it down to 5 or 6 steps, I think is a little bit, there are many more than that. But if you wanna just think about what happened, right? When we talk about this 10 years to build Vogtle, right? So from March of 2013, when the license was issued, to March of 2023, when it actually sort of went critical and entered commercial operation, you know, there was about a couple years before that they were actually doing a lot of work on the site. They got something called an early site permit, 2009, 2008. Um, and that whole idea was they couldn't pour any sort of safety critical concrete, but they could prepare the site, clear the site off, right? Prepare stuff for the balance of plant, for the non-nuclear side, and also begin, preparing the fill, as we call it, or the backfill that the plant will actually sit down. So at Vogtle, in particular, what we did is we dug down 100 feet right below the plant grade, down to a layer of clay, and then we rebuilt up to about 50 feet, right, with a sort of bed of safety critical fill. Right, that actually was regulated by the Nuclear Regulatory Commission because it impacted the seismic response of the nuclear island. And actually, even before we started the early, the actual licensed nuclear activity, we were already close to a year behind the scheduled construction, just because that process of actually filling the safety critical fill wasn't actually in compliance with the license, or the requirements of the early site permit. So this really gives you an idea of that even before we started the nuclear grade sort of concrete and construction pouring, concrete pouring and construction, we were already behind the mark on this project. And it also gives you an idea that that should have been actually a time that Westinghouse had the ability to really be catching up, but was just really falling way, way behind in every single way. So here we are. So we've done what we call, the sort of site preparation. We've obviously cleared it of, say, trees, of boulders. We've dug down to wherever the sort of base mat, we generally go way below the base mat. Maybe if if we're pouring directly on, or we're building directly on bedrock, we do rock inspection, right? But we generally do some sort of inspection to make sure that where we've dug down to is actually responding to the requirements that was assumed when the plant was going to be built. So if you look at the early pictures, for example, of the Vogtle site, they literally have sensors that are measuring, say, movement of the sort of of the safety critical fill and the sort of dense layer of clay that's beneath there, to make sure it's in sort of requirements that is necessary for the seismic sort of qualifications that we need the structure to be qualified to. So I guess you could call that sort of, rock inspection, or base mat preparation, just to make sure that we're actually building on literally a solid foundation on the earth, to make sure. So let's call that the first step, if you will. And that's, it looks like a big hole, but a very, very neat hill hole that needs to, meet a bunch of regulatory requirements as part of the, sort of safety basis of this plant. So, okay. So we have that. So I'm going to, yeah, go ahead. Do you have a question, Chris?
Well,
Sorry.
no, I mean, I'm just, we were both over in Dubai, and I was watching some videos afterwards about, the construction of the Burj Khalifa, the 380 piles or whatever that were driven into, through the sandstone. They actually run an electric current through the rebar inside of those concrete and steel piles, because there's salt water that's kind of seeping in and would erode the foundation. And if that electric current wasn't kept there with a cathode, sort of concentrating all the corrosion in one spot.
Galvanic, sort of.
Wild stuff that goes
Yeah.
into these, the world's tallest building, or in Vogtle, I mean, we're saying maybe it's one of the world's most expensive buildings, whatever moniker that it earns. But it is fascinating, because we do hear a lot, and I don't want to get sidetracked on this, but, people saying, hey, how will these things perform in earthquakes? And so getting a sense just of how, 100 feet down is a long ass way, and the ways that these things are seismically isolated, probably beyond the scope of this podcast, but certainly I love that description so far. So if you want to nerd out more on that, or move on to stage 2 of our more than 5 things, go for it.
To your exact point, right? I'm not going through everything else, but there's generally, depending on the, soil and the sort of bedrock and geology of the site, right? Generally, we do have to do a dewatering, it's called, as anyone who has done civil construction knows this, right? If you're going down below, say, the water table, right, there's a possibility that there's going to be a lot of, an aquifer or groundwater that's going to want to seep in. So often you do have, variously needle pumps or other sorts of pumps that allows this site to be dewatered and to be dry, right? And then we're basically filling it back up to about 50 feet. And then we begin the way that the AP1000 sort of, and this is very varying on from site to site, but one of the interesting things actually about the AP1000 is, at least for places that are not in the high seismic intensity. So the reference AP1000 design is designed for a reference peak ground acceleration, or PGA, of 0.3 g, right? And g, of course, is the gravitational acceleration, little g gravitational acceleration, which is 9.8 meters per second squared. So you can do that math, right? It's around 3 meters per second squared. And more importantly, in a lot of ways, right, there's what we call a spectra, that talks about the way that actually an earthquake will move the plant, right? It's not just the peak acceleration, but the distribution of velocities in different directions that the plant is seismically designed to handle, right? So given this standardized plant design that Westinghouse came up with, they came up with a reference base mat design, right, that sits over what we call a mud mat. Right. So what happens is we're at that 50-foot, say, roughly speaking, and I might be slightly off on the levels. I think that the actual base grade of the base mat is like 47 or 46 feet. You're below grade of the AP1000. So the idea is we pour a mud mat on top of that, whatever that safety critical, foundation that the plant is going to be built upon. And then and a mud mat, just so everyone knows, is an unreinforced bit of concrete, right? Like it's like you pour concrete, and basically with no reinforcement there, right? And it's just to give a flat surface upon which to start building the plant up. As its name implies, it's like, it sits on the mud, right? It's like a mat on top of the mud that we then sort of have a level concrete surface that we can begin the base mat construction of the nuclear island. Right. So maybe we want to start transitioning from there. And that's where we get into nuclear island license activities. Right. At this point, this will be a highly regulated activity that we will have to basically be, as we're pouring the base mat, pouring the foundation of the plant. This is going to be really, really important to the safety case, particularly the seismic case of the plant. So it's going to be highly regulated. And so we have to have a site license at this point, or a construction permit in the the United States sort of regulatory infrastructure to proceed to this point. So we poured this mud mat, and then what's really interesting with the AP1000 design is, of the six plants that were reactors that were licensed at multiple different sites in the U.S. One of the interesting things that we saw, none of those were particularly high seismic areas. They were all on the east coast of the United States, which is not particularly seismically active, although there is obviously some seismic activity. One of the cool things is that there might have been some difference in the mud mat design, but the actual base mat was standardized across all six, all six different issued COLs, and the NRC was able to basically say you can actually use the reference base mat design for the AP1000. That includes, of course, Vogtle and Summer, but it also includes licensed plants that were never get built, like Turkey Point down in Florida, right? It includes William States Lee, as well as Levi County, which are all different geographies, different states. But we were able to actually standardize even the base mat of the plant, right? Which shows, I think, not to be an AP1000 fanboy too much, but it really shows the robustness of the ability to standardize the plant, even in different soil structure interaction and different site geologies. So that's sort of where we've got it. And that base mat is sort of 6 feet thick, if I'm remembering right, for the AP1000. It's a highly reinforced concrete structure where even the details of the rebar are highly, highly regulated. And the tolerances that are necessary on that rebar are very, very regulated. One thing I will say that's interesting, if you think about it, what's really going on here is that that base mat is sitting basically on top of the mud mat. And so if you actually look at the safety case that's going on, they literally are doing analyses to make sure that the plant won't float up, right, from that base mat, and also doing frictional calculations to see how, in a seismic event, let's say the base mat of the plant is sort of shifting alongside the mud mat. And to the other point, there's generally is a waterproofing membrane of some sort that is put in between the different mud mat layers, as well as the sort of base mat. Am I going into too much detail? I have no idea. Like this, like I'm trying to explain to you
Yeah.
that even something as simple
Right.
Even something
It's
as simple as
illustrative.
coloring a base mat here is complex. I'm trying to do it. I won't go into, but we got into, not only did we get into problems with the regulator and with them sort of deviating from what the quality of the safety related fill is, and literally actually we get the first litigation even by 2012, 2013, we have Southern suing CB&I and Westinghouse because Westinghouse and CB&I are claiming that there's an issue here with the way that they're doing the safety critical fill, and Southern says it should actually be your responsibility based on the contract that we signed here for you to actually be able to meet this. And they're suing for like $30 million, $38 million. They were unable to sort of reach a non-litigation based settlement. So they literally go into court to begin actually fighting this out based on this issue that we have just in the safety critical fill that needs to be before we even begin nuclear safety, sort of regulated construction, right? We already are in an acrimonious relationship between the three sort of parties. So I'm not trying to. I know probably people are like tuning out here. What I'm trying to say is these things are not only important from like being pedantic and being really nerdy about it, but they're actually commercially really, really important for everyone to understand what is necessary for building a nuclear project. Because literally these parties are going to litigation before we think of this project being in any trouble in 2012, 2013 over issues before they even begin nuclear safety construction. And this is maybe why I have expressed not doubt or hesitation, but just a note of concern or of something that people should be aware of when we're talking about even SMR projects that require such huge civil infrastructure to be built. It's really important that we drill down and understand that these can be drivers of both cost and schedule overrun even before we get building it. So when we're looking at the BWX 300 and we're talking about a big shaft that goes way, way down of all nuclear related sort of safety concrete that maybe have to be down 140 feet or 130 feet below grade, that's something that we should be, sort of flagging. Same thing with, of course, NuScale, as we previously talked, which had a much larger and almost equally deep sort of civil structure below grade in order to deal with the aircraft impact assessment role in Australia as part of that design. So these, I know, sound the devil is in the detail in nuclear projects, and I'm trying to bore your audience almost to sort of emphasize how sort of detail oriented this process actually is. So apologies to everyone out there who is no doubt saying, why is he talking so much about the base
I
map?
think decouple and the relative wonkiness and nerdiness of the podcast has already filtered out a lot of folks that might have been turned off by that. So that was good. I think it's just a matter of the interest of time. But again, I think as you're saying, very illustrative. I don't know if it's possible. I don't know if it's possible, but if you could again just try and walk through a few
Go
more
ahead.
other stages with a little less excruciating detail, unless you want to make some pit stops for again other things that came up. I'm not sure if this is the best way to organize the episode, but again, I just would love to have that sense of
Well, I kind of like this because I think we're kind of doing an abbreviated fast sort of through staging. So we begin sort of, so if you think about a nuclear project from a 30,000 foot, level, there's the improvements, sort of the work to get the site prepped and ready for actually, that's digging down, getting down, doing rock inspection or fill inspection, doing some safety critical fill. So you have a nice base to basically build the plant on. Then we begin the actual process. And once again, I'm focusing on the nuclear island. I'm not focusing on the turbine island and what needs to be done in the circulating waterworks. So if you think about it from a labor perspective, obviously we have manual labor that's helping with all of this products, but processes. But we have basically, the thing that we're going to build as we're building the base mat, which is the foundation upon which we're building the plant. We're using, experts in civil works, construction, concrete, rebar. That's sort of where we are at this stage right now. As you'll know, right, we're going to have to finish that up. And then we're going to have to not only continue building the plant up, but at a certain point, we're going to have to start actually doing the HVAC, the sort of welding, the piping, right, and the electrical work that will be necessary to actually build the components and assemble the components that make up the nuclear steam supply system. We're not even there yet, right? We're still at the point upon which we are building the foundation of the plant so that we can actually build that nuclear steam supply system and assemble it onto the sort of foundations of this plant that we're building right now. But at Vogtle and at Summer, we begin to have an initial problem right away, which is that as part of, as I said, the base mat is highly, highly regulated because it's so critical to the seismic response of the plant in a design basis earthquake, right? So as part of the license, Westinghouse and the licensees had to basically submit tables and design information that contained the details, for example, of how the rebar was going to be designed and configured, right? And what we saw in that plant in this build was the rebar, specifications that the applicant themselves submitted to the NRC. That was part of this one-step licensing process, which basically said, okay, you're going to tell us how that rebar is going to be built. We'll do our safety you'll do a safety analysis. We'll evaluate that safety analysis. And all you need to do is build in conformance with how you said you were going to build the plant. And we begin the first series of mistakes that occur here that require license amendments. What turns out being the case here is that it turns out for a minor, very minor detail in the tolerances and in some cases the actual design of the rebar that was actually fabricated and placed at the plant actually deviated from the way that Westinghouse, Southern, and CB&I told the Nuclear Regulatory Commission they were going to build it. And the NRC inspection force flags this issue and says, you're out of conformance with your own license. How do you want to deal with this? In some cases, I'm not going to go into excruciating detail because it would bore the audience. In some cases, we literally had to jack out a lot of that that rebar, that foundation, and basically redo it in conformance with the license. In other parts of the base mat, we had to work with the Nuclear Regulatory Commission to basically change some parameters, particularly the compressive strength of the concrete, to be able to deal with the fact that we had non-compliant rebar placed by the licensee themselves that violated what they themselves had told the NRC they'd be building in design, in spec with. So we get to this exact idea of one of the downsides, like with the modular construction of this one-step licensing process, is it really assumes that you have a very, very rigorous quality assurance and quality control sort of, in place for both your designs and your procurement and your placing to make sure everything's in conformance with the way you say you're going to build the plant. But if you don't build the plant in the conformance with the license that you yourself submitted, you're going to have a problem. And you're going to need, license amendments or some sort of design change or replacement of the actual component to be able to sort of build the plant up.
And I mean, I've seen some video. I think it was Hinkley Point of this rebar. I mean, it almost seems like there's more rebar than concrete. It's just an incredible amount of steel. And so the issue was just the angle at which, was it just the angle at which it was laid? Because I hear people saying, hey, the NRC should just kind of go easy on these guys. Does it actually make any difference in the end? Just let it go. What's your perception there?
So there were a half a dozen. I mean, I can go through I don't want to walk through. There were at least, I think, a half a dozen license amendment requests that were required to basically get the rebar and concrete into spec. Here's the issue. And some of it had to do with, for example, the way that the NRC versus the licensee were interpreting American Concrete Institute codes on actually how the rebar was going to be in compliance with that code, just to give you an example of the sort of minutia that's involved here. Here's, I think, the takeaway for this podcast that you would want to say is that most of the issues, I would argue maybe even all of the issues here, the NRC is basically saying we are holding you to the standards you yourself set up in the license, right? The license criteria that were put here were put not by the NRC, but by the licensee. The licensee said, NRC, this is what we're going to build into. Is this yay or nay? Do you like this or not? And the NRC said yes. And then it turned out, for example, on some of these issues on leveling the sort of base mat, it turned out that they said they were going to be within a certain tolerance. And it turned out the actual build was a lot less tolerant when we actually tried to do this in the real world. And they had to go back to the NRC and say, we're out of the sort of tolerances that we were ourselves said we were going to build to. And that's where I think here's the sort of pro-nuclear, the sort of bull nuclear case now, is because we've actually, a lot of these issues yes, were caused by the lack of design finality. So it turned out how actually, perfect, how actually we were going to able to meet the licensing requirements in one case was a lot of times was just driven by the fact that, we couldn't actually build it as the license sort of specified because the design wasn't complete. We weren't able to accurately simulate what that design would look like in reality because it wasn't done when we submitted the license. In other cases, it was just practical sort of constructability issues. Westinghouse hadn't constructed a plant in a long time, right? CB&I and Stone and Webster had really not constructed a plant and not done the civil works on a nuclear plant for a while. So their expectations of the tolerances and quality that they were actually going to be able to build was much higher than it was in reality. The good thing here is we actually have that experience. We have all that licensing material. So if I was building an AP1000 today, I would basically say, okay, I learned all of these license amendments from Vogtle that you approved. I'm going to make sure that I'm able to build to the actual real world expectations today before I start building. And the one-step licensing process allows us to do this. But it really does point to you got to know your design well. And not only do you have to know your design in silico or on blueprints or on paper, you got to think about the practical ways that you're going to construct the plant in the real world, which is going to be a lot less perfect, and design that into your licensing basis before you sort of make yourself held to overly stringent quality control, quality assurance sort of targets or tolerances in the licensing basis. I'll say one more point about this. One of the interesting things I think that we have learned, that a huge credit to GE Hitachi, is there's a reason why GE Hitachi is not building the first BWX 300 under this 52 one-step process. They're doing a construction permit, two-step licensing approach for the first plant. They're going to learn all the practical lessons that we get from building a plant in reality, constructing it, and then maybe, if their regulatory engagement plan is to be believed, turn it around and then do a design certification and a sort of licensing basis under one step so that they actually can have that real world constructability, a final design and real world design basis together so that they can have a one-step license that actually is buildable.
Okay, so I'm getting a no,
Is
no,
this
I'm
too
getting it,
much?
and maybe
But these are really
right,
important lessons,
and
man. I gotta say, I hate to tell you that the real world of nuclear construction is not a pretty
no.
one, and it's slightly
It doesn't just,
boring.
like, you're just so used to these, like, CAD illustrations, these animations on PowerPoints that I see all the time, but, I think we've spent probably a time that's appropriate to how long the civil works elements take. And I'm curious to, like, how much, and we're gonna go through some of the other main sort of chunks of processes, the civil works, the NSSS, et cetera, balance of plant, whatever contain however you wanna break down those other 5
Piping,
or
yeah.
6 sections, 10, 50 sections. Um, but it is going to be curious to see. Okay, well, on the civil works side, was Vogtle a huge anomaly compared to the average nuclear build? Like, what sections of the build went over time and over budget, or is it just Murphy's law and just literally everything that could go wrong went wrong at every stage?
So I want to say two things here. The first is Vogel 3 and 4 was not a particularly long build. Well, it was a longer build in the United States sort of history, but Vogel 1 and 2 actually took longer to build than Vogel 3 and 4. Less expensive, but longer. And a lot of that, in fairness, on 1 and 2, a lot of that was the NRC's fault. Vogel 1 and 2, where it's being built sort of post TMI, it was one of the longer builds in US history. But we have a lot of long builds in the United States' nuclear construction history. So I want to be careful here in saying that everything that went wrong at Vogel did go wrong. That's actually kind of true. We saw challenges, as we'll talk about, in almost every aspect of the build that we had, which in some ways may have been expected because this was the first nuclear power plant that we started construction, that had been ordered since literally 1978. That was, and slightly before that, that actually beginning construction. So maybe that's not so surprising. What the note of caution I will just tell everyone here, I will tell the audience is, let's go back to the Chinese control example, right? The nuclear power plants that China is building, they're all, with the exception of the VVER product line, right, which is Russian, Rosatom, obviously, they're all derivatives of American or French nuclear power plants. So even the Hualong One, the so-called indigenized sort of Chinese nuclear power plant, nuclear steam supply system, its history, of course, if you look at it, and it's not a secret, it's based on the French three-loop pressurized water reactor, the sort of CPY series, with changes. And that, of course, is based on the American Westinghouse three-loop product line at Beaver Valley and at uh, I'm forgetting the name, the Virginia plant that's North Anna. And so those plants, though, are coming together in China in 5.5 years. And they have as much civil works, actually slightly more civil works than, say, an AP1000 project did. Here's the point. Despite the fact that China is able to, on a median, so 50% are building faster than this, 5.5 years of nuclear construction with all of that civil works, with a more classical sort of base mat and containment design, the Chinese builds took 9.4 years for the AP1000 and maybe a little bit slow, 8.5 years on Haiyang 2, right? So these were much, much longer, standard deviations, multiple standard deviations longer, even in a workforce and a country that is very, very experienced in nuclear civil construction. So there was really issues and challenges that were AP1000 specific. Now, on civil works and civil construction, the Chinese plants were actually on time and on schedule. So they actually did get that far, but then they started hitting other challenges that weren't associated with the base mat construction. So that's just what I want us to be clear here, is that we have had building problems of nuclear power plants going back decades. And in the United States, and this build in particular was problematic even for very experienced builders. So let's move on sort of from the base mat sort of construction, right, into where we're starting to begin building the actual, containment, the safety critical welding that's going to be needed, the piping modules, and so on. So one thing I want to just go before to your earlier point, before we move off of concrete, I'm sorry to belabor the concrete issue. You were correct at saying that the rebar is very, very dense in nuclear power plants. One of the general, issues that we see is problems called consolidation in concrete, the ability to make sure that there aren't voids or pocketing within that very heavily dense rebar. And so this is not trivial. And this is something that is really, really important in nuclear power plant civil construction and concrete work and concrete engineering. And this has been a challenge that we said. One thing that should work in the AP1000's favor and disfavor designs like NuScale, for example, or the EPR, is that the actual safety critical footprint of that nuclear island is much tinier than we historically see large, mainly because of the passive safety system. So it should be better. But obviously, in this case, we're already in trouble here. We're already behind schedule before this even happened. So, okay. So we're starting to build basically the structural modules that consist of the sort of AP1000 as we start building up. And we begin starting to see major license amendment requests that are having to basically fill in to basically be able to build on top of this base mat that's happening. But before we go into the regulatory challenges, remember how we started this podcast about all of the problems that we had with these modules that were coming? All of a sudden, this is the point of the construction that we're starting to get in trouble because of this. So CA20, it's basically the entire auxiliary building, including the spent fuel pool, right, is in this one mega 1,000 metric ton module that obviously is going to need to be placed on the base mat, placed into concrete, sort of, integrated in. Here's the problem. When those submodules haven't gotten to the module assembly building or have gotten to the module assembly building and need to be reworked on site to basically be able to get up to the QA that's needed to be built, we're all of a sudden starting to run into sort of scheduling issues because maybe we've built the base mat up, but CA20 may be 2 years or a year late in actually being placed onto onto the actual base mat. So all of the advantages of modular construction, where we're supposed to be snapping things on, this is where we start really getting into trouble. And then we begin to actually do the sort of 4 major areas of craft nuclear construction that we're doing. So in nuclear projects, we generally distinguish between what we call craft labor and manual labor. So craft labor are going to be things like electricians, like HVAC technicians, welders, etc., that have a very specific skill set and a pretty amazing artisans that are going to be able to actually do this really, technically challenging issues in actually assembling the plant. Whereas, shit, man, we're already at
It's
12:55.
all
I'm
good.
just
It's all, there's
realizing
going
that
to be a
I've
part.
got
It's
we've
this
got
part
a
three. It's no problem.
oh fuck, man.
Carry on. Carry on. This is good.
uh, I just looked at the time. I'm still at the foundation.
It's all good.
I'm sorry. I'm sorry.
No, no, carry on.
um,
Honestly, don't
uh,
skip a beat.
no. It's okay. It's okay. So we're starting to see those challenges really start piling up on the project, and we're also beginning to see that the detailed work packages that are being distributed out to the work phase, to the work teams of craft laborers and manual laborers, right? That have to go in and actually literally do, build a structure, pour some concrete, do a weld, or assemble a cable tray, right? They're starting to realize the work teams are coming back and literally realizing that the work packages that they're being handed over are unbuildable, right? That there's literally they're physically unbuildable because the design hasn't been finished at Westinghouse headquarters, let's say, or at CB&I headquarters, and the construction may be 3 or 6 months ahead of where the engineering bases are. So we literally have the cases where work teams are literally attempting to build this plant, and they're months, but like they're literally waiting around for weeks and weeks and weeks, right, to be able to actually build the plant out, because they have to wait for it to be redesigned and get an engineering design and change review that has to go all the way back up to the headquarter, sort of engineering company, and be re-engineered and reissued to the spot. So you have all these high-priced laborers, right? One of the things we love about nuclear construction is these craft laborers are very expensive, right? And that's really good for them because they get high wages. This is a skilled artisan job, right? Which we want them to be properly compensated. But it becomes even more expensive when all of a sudden you don't have the actual buildable work package that actually can be built. Now, this is one of the challenges that we have with first of a kind builds, but it's one of the things that why it's so important that we build an AP1000 today, because we know we have work packages that are buildable because we built them. And so this sort of major yeah,
No, no,
go ahead.
I mean, just as a slight tangent or offside here, I'm thinking about this project like almost like a war, and the incredible complexity of that project delivery. It's like you have a general, you have marshals, you have like a whole communication structure things need to move down, and you have the morale of your soldiers, and these craftsmen sitting on their hands for days, weeks at a time. I mean, I can imagine the lunchroom conversations and just you wouldn't feel particularly as motivated as you might if you lose faith in your commander in chief kind of thing, right? I don't know. Like, I don't know if that's an appropriate analogy or if that was a major factor, but it's just on the human
Yeah,
side, I can just imagine.
I mean, one of the issues that we had here at this project, let's just be frank, was retention of the skilled labor force over this massive time. And part of that was compensation, part of that was shortages of, workers that were highly skilled that were needed for other projects in the region. But another problem, as you just said, is that problem is going to be compounded if you're not able to use the labor force most effectively in terms of actually getting project completion, actually, getting a work package actually built. If people are just literally sitting around because they're waiting for the work package that was supposed to be buildable redesigned so it can be built, you start seeing how these problems start piling on, even as we start building up from the foundation and start doing more craft labor, more welding, and more electrical work. Now, let's go back to what's going on at the project level. So everyone's realizing this is 2013, 2014. We're way behind schedule. We're not getting the sort of project completion rate that we're needed as part of the sort of master project schedule. And there's a problem here that Chicago Bridge and Iron has bought. And the old joke is, of course, that Chicago Bridge and Iron doesn't is not based in Chicago and doesn't build bridges. But Chicago Bridge and Iron buys the old EPC, which is the Shaw, which is building it, and then all of a sudden looks at this project, figures out that it's a fixed price contract for the plant and realizes this is a massive, massive liability that the company has on its books to finish this project that is not going very well. So this is both CB&I, this is both Summer and Vogtle at this time, are both being built, and they're both way behind schedule with a really, really steep road ahead of them. So the commercial issues begin piling up, which is that there is tension between Westinghouse and CB&I, tension building between Vogtle, between Southern and SCANA as the customers and the consortium, and basically everyone is beginning to threaten to sue each other. And the first person who sort of really starts going out is Chicago Bridge and Iron. Basically says, "I want out. I want to quit. I want to get rid of these liabilities. How are we going to do this?" And they propose at this point a deal where Westinghouse itself buys the old Stone and Webster division of Shaw slash CB&I to basically buy it up and sort of assume the entire project themselves. But that means not only is Westinghouse going to be responsible for the nuclear sort of scope of this project and the nuclear engineering scope, they're going to be responsible for the entire delivery and assume all of the roles of the EPC. And remember, at this time, Westinghouse is backed up by Toshiba. It's owned by Toshiba. So there's this idea that Toshiba, well, we are very experienced in building stuff. Toshiba is going to take on this sort of all this risk and all the completion responsibility. And that's where we start beginning and get into a little bit of challenges here. How's the internet connectivity going? But so I
Internet is
want to just
good.
maybe
Yeah.
end at that point. I want to end at this point and basically say, maybe we need a part 3 because we're about to watch Westinghouse go into bankruptcy, right? Toshiba almost collapse as a result of this, and a rapid succession of 2 new EPCs that are going to be assigned to finish this project up, with the last one being Bechtel, who ultimately finishes this project, and with the project management being ultimately assumed by Southern, and SCANA abandoning the project mid-place. So it gets exciting, but we're 50% complete maybe at these projects, and things are going pretty bad.
Right on, James. Yeah, I mean, I have a feeling there's going to be more than just an episode number 3, but I'm personally loving it, and we'll let the audience decide. So if you like this show, get some audience participation. Let us know about it on Twitter. Demand a part 3 with James Krellenstein on the Murphy's Law Vogtle. Okay, James, thanks again. Got to run off to an appointment, but it's been a pleasure, and we'll get the internet issues
Yep.
fixed for next time.
Cool. All right.